So here I'm just going to wrap up the last few of the indicators so we can move on to the communication piece in class. Um, for this particular part, we already talked about glaciers and declining snow and declining glaciers. And we're just going to wrap up by talking about the Arctic sea ice and a few other indicators. So the data here come from satellite images, and the data has been very clear about area covered by sea ice in the Arctic getting smaller. You can see down here, this yellow line is the average minimum sea ice, which usually happens in September. The average between 1979 through 2000, and this is 2012, which was a particularly low sea ice year. And you can see that here. Here's 2012 right here. These are the data between 1979 and 2017. Really clear downward trend. Sea surface temperatures have also been increasing, as you guys know, probably have heard. These are the data here. Oops. And here you can see the anomaly is 0. The average there is 1971 through 2000, and below average previous to that, but now trending upward over time, particularly since about, say, 1970 or so, 1980. And then the data here come mostly from satellite sensors and thermometers on ships and buoys. Sorry. Ocean heat content has also been increasing. And in fact, this is where the majority of the warming is going. And this was sort of an interesting thing here. You can see this red line here is the average heat content in the surface of the ocean. When they're saying surface, they're talking about the top 700 meters. And then the black line is the 0 through 2,000 meters. And so people were confused for a while because they didn't see a huge increase in ocean heat content, but then they found out that was just because they weren't looking quite deep enough. So this really is where the vast majority of the heat that's getting trapped in our planet system is going. This is just a graphic to try to get that point across, sort of a nice one, I think. More than 90% of the heat going into the ocean, much less going into all of these other things like melting the ice sheets, into warming the continents, the land itself, and the atmosphere. Global sea level also rising, as I'm sure you all are aware. But here's some data and some interesting sort of bits about how sea level is changing over space. The data here comes from tide gauges and satellites measuring the distance from their orbit to the ocean surface, and both of these data show that global sea level is getting higher. This is global average sea level change, and really clearly going straight up. The yellow is the tide gauges, and the blue here is satellite measurements. So that's the global average. And why is it rising? You guys covered some of this in your presentations. Worldwide, we've got 8 inches higher than in 1900, but it does vary with location, and this has to do with a lot of different things like ice age effects, which I'll talk a little bit more about in just a minute, or right now. And this has to do with what's called isostatic rebound. So when glaciers cover the Earth, they're very heavy, so they actually push the Earth's crust downward into the mantle, which is more plastic, more compressible. So the heavy glaciers here push down on the crust, and so that kind of sinks down, but right before the glacier, that part of the land sort of pushes up, and they call that the forebulge. This is one example in Scotland and southern England. This also happened in the northeastern US, where glaciers pushed down parts of Canada, but right in front of those glaciers we had sort of a forebulge that popped up And this happened sort of in the Chesapeake Bay area. So this is called isostatic rebound. After those glaciers melt, this land over here sort of rises slowly, slowly, slowly back up, and this land sinks back down. So when the glaciers melt, the land rises up, and this is happening, as I said, in northern Canada and also in places like Scandinavia. And the forebulge subsiding happens also after the sea melts, or after the glaciers melt, and this is happening in southern England and also in the Chesapeake Bay area in the U.S. And this is just kind of showing you where our ice sheet was in the U.S. This is the glacial maximum, so you can see this area, particularly up here, is sort of rising back up, and then down in this area here, Chesapeake Bay area, and others, those parts of the land are sinking back down as the forebulge kind of depresses. Okay, so that's one reason why, for example, down in the Chesapeake Bay area, sea level seems to be actually rising much more quickly, because that land is also subsiding. But there are other reasons why land might subside, and one of them has to do with oil and gas extraction causing land subsidence. And this is basically happening sort of around this area of the world where we're taking a lot of oil out of the crust of the earth, but this is the crust of the earth that's slightly under the ocean. But you extract all of this liquid and you leave air in its place, so that land sort of sinks down into where that oil used to be. So this is happening in the Gulf of Mexico, where the sea level is rising much faster in some areas than in others, particularly where there's a lot of active oil and gas extraction. And you can see that kind of looking across these different areas. These are tide gauge data. So this is Grand Isle, Louisiana, which is really close, sort of right in this area of heavy extraction. You can see sea level rising really quickly, 9 millimeters per year. Galveston, Texas, a little bit less, but still relatively high, about 6 millimeters per year. But Pensacola, Florida, where there's not very much oil and gas extraction going on, much lower, about 2 millimeters per year. Okay, so we talked about ice age effects, oil and gas extraction. There are also impacts of prevailing winds, whichever way the wind is pushing sort of water toward or away from land, that has an impact. And then also ocean currents. We've talked a little bit about the slowdown of some of the large circulation of water, also the slowdown of the Gulf Stream, fresh water kind of making that water less dense. So instead of sinking, it kind of piles up along the coasts. Another thing that we talked really briefly about was that the Greenland and Antarctic ice sheets are so large that they actually have a gravitational pull on the water around them. So that water sort of piles up around Greenland and Antarctica. And if they melt, the water there will redistribute more evenly around the world, so that right at Greenland, for example, sea level will actually be a little bit lower than it is right now. Okay. I think I've talked about this before in class just because it's kind of interesting, but sea level rise is rising faster than average in the Northeast. So this is not where that forebulge is subsiding. This people think has to do more with the fact that that large circulation current in the ocean is sort of piling up instead of sinking. Largely, they think because of inputs of fresh water making that salty water less dense, sort of piling up around the Northeast instead of sinking down to the bottom of the ocean around Greenland. Okay, so lots and lots of indicators of a warming world. Increases in air temperature over the ocean, over the land, across the entire troposphere. Increased seawater temperature and ocean heat content. Declining stratospheric temperature, increasing humidity, and also decreasing snow and ice, glaciers, sea ice, and snow. So up here, this has to do sort of with increasing temperatures, and then those increasing temperatures are really the things driving these other indicators. So one thing that you guys should think about for the little assignment that I'm going to have you guys do for this part is which of these are also feedbacks on temperature. So we know that temperature sort of makes these things happen, but then what are the feedbacks on temperature? Are there feedbacks on temperature of any of these things? Okay, so in the next video, I'm going to talk about some other indicators that you might hear more about in the news, but are a little bit more complicated, like extreme events, changing migration patterns, and changes in the growing season.